This is 4.8 part 2. Okay, so I left off with that first video and we are actually on page number 4. So this is example number 2, and really quick before I start talking about it, remember that this section is supposed to be covered over 2 days. So there's going to be quite a few videos to finish it out. So I'm just forewarning you, if you're trying to get done with it in one setting, it might be best to break it up a little bit. But at any rate, example number 2 says, find the antiderivative involving ln of x, a to the x, and inverse trig functions. So we're going to look at these. By the way, with this first one, I want you to note that you can break up a binomial as long as it isn't squared into parts. So you can do the integration, and sorry about that, I don't know what happened there. The integration of 5 over t dt plus the integration of 1 over the square root of 1 minus t squared dt. So you may be tempted to say, okay, well, I'm just going to rewrite this as 5, kick the 5 out, and then rewrite this as 1 over t dt. And that's exactly what I would do. Okay, so you would think for the first one that I would use rule number 1, but rule number 1 does not work for anything that's t to the negative 1. So if you have anything like x to the negative 1 or t to the negative 1, you can't use rule number 1, okay, because it won't work. Because remember, rule number 1 says we do n plus 1 over n plus 1, right? So if I did that, here's what would happen. I'd get negative 1 plus 1 over negative 1 plus 1. So basically I get x to the 0 over 0, which is 1 over 0, which doesn't work, right? So that's why we cannot use rule number 1 for anything that is to the negative 1 power. But there is a rule for this. So if you look through your page 2, you will see that there's a rule involving that says the rule is the integration of 1 over x dx equals ln of the absolute value of x plus c, okay? And the other rule that we're going to use for this one, and by the way, that was rule number 10, there's another rule that we can look at. It's rule number 13 that matches up with that quotient 1 over square root of 1 minus x squared. Okay, so if you take the derivative of that in terms of x, it's going to equal inverse sine of x plus c. Okay, so let's go ahead and use rule number 10 and rule 13 to figure this out. So the first one, we have 5 times integration of 1 over t dt. So I'm going to write this up as 5 times ln of t. And then I'm going to integrate the second piece, which is integration of 1 over the square root of 1 minus t squared. So I know that equals the inverse sine of t. And then I have to tack on the plus c to my answer. Okay, so that's A, and that's using different rules that we haven't seen yet. In part B, we also have a similar situation where we haven't used any of the rules because we're supposed to integrate 2 raised to the x power plus 1 over x times the square root of x squared minus 1. So I'm going to integrate 2 to the x dx plus the integration of 1 over x times the square root of x squared minus 1 dx. All right, so I need to find some rules that match up with this. So once again, I'm looking on page 2. I see I have rule number 12 that looks like the first bit. So the integration of base, which is a constant, like in this instance 2, raised to the x power dx, equals the base to that power over the natural log of b and then plus c. Okay. The other rule that we're going to use for the second one is rule number 15, which says the integration of 1 over x times the square root of x squared minus 1 dx equals inverse secant of x plus c. So once again, just a word of warning, if you have something that looks like a quotient or a product, if there isn't a rule for it, then you can't do it. Okay, not at least in this class. You will be able to do them later with integration by parts. But I'm just giving you a word of warning again. Make sure when you're doing these, there's a rule for it. So let's look at the first one. There is a rule for 2 to the x. So if I integrate that, I get 2 to the x over ln, and the base is 2. So ln of 2, and then plus c. But I have a second piece, so that's why I'm not writing up the plus c right now. I have to integrate 1 over x times the square root of x squared minus 1. So once again, there's a rule that matches that up, and it's the inverse secant x. Then I tack on the plus c to my answer. So that's how you do a and b. So once again, those are using logarithms to figure out how to take the integration of it. So on the same page, we're still on page 4, it says it is legal to separate the integral of sum or differences of terms into sum or difference of 2 or more terms. It is not legal to separate the integral of products or quotients into their products or quotients of 2 or more integrals. So once again, we don't have a product rule or a quotient rule for finding integration. Okay? So here's an example of something legal. If I have a polynomial function or 2 terms that are added together or subtracted together, then I can break up the pieces and take the integration of them. If I have 2 functions that are multiplied together and I don't have a rule for it, then I cannot break it up into different pieces. This is no good, okay? No bueno. So these 2 I can't do, and same with quotient. I can't break up the quotient like we used L'Hopital's rule. Can't do that, okay? So once again, you have to be careful with integration. Make sure that whatever you're trying to integral has a rule that looks exactly like it, okay? Please note that there are very, very few rules of the 9 antiderivative formulas that contain products, quotients, or powers. Only rules number 8 and 9 contain a product, and we're going to write those 2 on the next page. Only rules 10, 13, 14, and 15 contain a quotient, and only rules 3, 6, and 7 contain a variable expression raised to a number power. Okay, so we're going to look at all 3 of these and write these down. You should have them in your notes just to kind of reinforce the learning. And if the integrand contains a product, quotient, or a power that does not match one of the 19 antiderivative formulas, then you must manipulate it until it does match it, or you're going to use some other methods. So we're going to learn 2 of these 3 methods in this class, and then you're going to learn the third one in Calc 2. Simplify the integrand using algebra or trig. We'll be able to do that in this class. Using substitution, we will be able to do that in this class. Using integration by parts, you will learn in Calculus 2. So we will not do that in this class, okay? So once again, these are for integrands that contain products, quotients, or powers that don't match any of the 19 antiderivative formulas. So let's write down the rules containing products. So on that page, it said we should look at rule number 8. Rule number 8 says the integration of secant x tangent x dx equals secant x plus c. Okay, rule number 9 says the integration of cosecant x cotangent x dx equals cosecant x plus c. And number 10 which is actually starting the quotient rules. So let's go ahead and write these down here. So rule number 10 states if I have the integration of 1 over x dx, it's going to equal the ln of the absolute value of x plus c. Here's another one that has a quotient in it. Rule number 13 says we have 1 over the square root of 1 minus x squared dx. That equals the inverse sine of x plus c. And rule 14 states that we have the integration of 1 over 1 plus x squared. And we haven't seen this one yet. But if I take the integration in terms of x, I get inverse tangent x plus c. And then finally 15. 15 is also looks like a quotient because we have 1 over x times the square root of x squared minus 1 dx. And that's going to give us inverse secant x plus c. Okay, so those are the rules containing products, rules containing quotients. And finally, we have rules containing powers. So this is rule number 3. Rule 3 says the integration of x to the n dx equals x to the n plus 1 all over n plus 1 plus c. And we've used that rule several times. Rule number 6, excuse me, not 4, but 6. Rule 6 states that we have the integration of secant squared x dx. And that's going to give me tangent x plus c. And rule number 7, the integration of cosecant squared x dx. What does that equal? That equals cotangent x plus c. Okay, my advice to you with all the rules is to make flashcards, and you're going to have to memorize them. That's the only way that this works. Okay, so make sure that you're very careful. Once again, be very cautious if you are trying to integrate something that has a product or a quotient or something with a power. Okay, so those are the, look out, the formula better match or else you can't do it. Or you have to try to do something else to make it work. Okay, so if we look at example number 3, find the indefinite integral. And by the way, this is page 5. I'm looking at this and I have t plus 1 in parentheses squared. I do not have a rule to make this happen. However, I can use some algebra. Because if I write t plus 1 times t plus 1, I can go ahead and distribute that. And then I'm actually integrating t squared plus 2t plus 2. Okay, now I can do that. So literally I'm integrating t squared dt plus, I'm going to kick the 2 out because it's a constant. I'm going to integrate the t plus, I'm going to integrate the constant 2 dt. Okay? All right. So, and by the way, that shouldn't be a 2. That should be a 1. So let me fix that really quick in my notes because I expanded that incorrectly. Okay, so let me just put 1 here, and now we are good to go. All right. So we're going to do rule number 3 for the first one. Rule number 3 states if we integrate x to the n dx, what are we going to get out of it? We are going to get out of it x to the n plus 1 all over n plus 1 plus c. Okay, so for the first one, I'm going to do that. I get t to the second plus 1 over 2 plus 1. Now for the second one, I'm going to take 2 times. This is a different rule. This is the same rule number 3. So it actually isn't a different rule, but we're going to apply rule number 3 to it. So we're going to do t to the first power plus 1 all over 1 plus 1. And by the way, you can use rule 3 for any power ones except when it says to the negative first power. You can't use rule 3 for that. Okay, and then rule 1. So rule 1 we're going to use on that last bit because integration of 1 dx equals x plus c. Okay? So in this case, we're dealing with t's, so I'm going to put plus t, and then I'm going to tack on the c to the end. Okay? So what does this look like? This looks like 1/3 t to the third. And then the 2's will cancel each other out to get plus t squared, and then plus t plus c. So this would be my answer for number 1. Okay? If I look at b, there is no rule that will allow me to do this, but I can use algebra again. So what I can do is look at that function and write it like this. So what I'm doing is I'm dividing by a monomial so I can split it up into pieces. Okay? So if I rewrite that, I can use the rules where I take and I subtract my power, so 2 minus 1/3. So let's write that out with a common denominator. So 2 becomes 6 over 3 minus 1/3. That's going to be x raised to the 5/3 power. Okay, so that's what the first one's going to be. And then I'm going to write this as negative 6 x raised to negative 1/3 power. Okay. So this is what I'm going to actually integrate. And like I said, I just used some algebra and some exponent rules to get there. Okay, so for this first one, I'm going to use rule number 3 for both of them actually. So I'm just going to put a little note, I'm using rule number 3. So let's go ahead and do this. So this first one is 5/3 plus 1 over 5/3 plus 1, and then minus 6 times, and then we're going to apply the quotient rule. So x to the negative 1/3 plus 1 over negative 1/3 plus 1. Okay, and then plus c. So what does this look like? We get x to the 5/3 plus 3/3 all over the same thing, which, by the way, this becomes 8/3. Okay, minus 6, and then we have x to the negative 1/3 plus 3 over 3. That's going to give me a positive 2/3. So I just have to clean this up again. So this becomes 3/8 x to the 8/3 minus, and then if I flip over 2/3, I get 3/2. And 2 goes into 6 3 times. So 3 times 3 will give me 6. Okay, and if you really want to check it, it looks like this. And that actually gives me 9. So maybe it's good I did check it right. So minus 9 x raised to the 2/3 power plus c. Okay, so that is the answer for B. Let's look at C together. Okay, I do not have a rule that looks like this, so my advice to you is write this out in terms of sines and cosines, right? So cotangent is actually equal to cosine x over sine x. And cosecant is 1 over sine x. So if I rewrite this, I get cosine x over sine x times sine x over 1 when I turn this into multiplication. So the signs will cancel each other, and I'm left with just cosine x when I simplify it down. Now I'm good to go, because if I take the integration of cosine x dx, I can look at one of my rules, which is rule number 4. So the integration of cosine x dx equals sine x plus c. Okay? All right. So let's look at this next one. Do I have a rule that says tangent squared x? I do not. Okay? But I can use the Pythagorean identities, because the Pythagorean identity says tangent squared x plus 1 equals secant squared x. Okay? So if I substitute in for tangent squared x, I can rewrite tangent squared x as secant squared x minus 1. Okay? So if I take and integrate secant squared x minus 1 dx, I can do this because I have a rule for secant squared x. So I can break this up into two parts. I can integrate the secant x dx and integrate the 1 dx. And I should have a little dx in there. So when we do this, I look at the rule, and if I look at rule number 6, and let's write this one out, the integration of secant squared x dx equals tangent x plus c. Okay, so if I integrate secant squared x dx using rule number 6, I get tangent x. And then if I integrate the 1, and remember we did this before, this is actually rule number 1. So rule number 1 says integration of 1 dx equals x. And then I have to tack on the c to my answer because I have a whole family of answers with indefinite integrals. Okay, I'm going to stop the video. That is part 2, and there's going to be more.